Hello. So let's look at an example where we can use the ideal gas law and relate the amount of gas that forms from some chemical process to information about a starting sample. So what we have here is we're told a 50-gram sample, which is a mixture of sodium chloride and magnesium carbonate, was heated, and then 10 liter of CO2 was collected at the given pressure and temperature. How many grams of sodium chloride was present in the original sample? So let's start by looking at what the situation is, how the process happens, and then what information we're granted or given from that. So the first part is we're told we have a sample, right? So we have a sample, and this sample has two parts. The one part is, let's do it the other way around. The one part is sodium chloride, so NaCl, right? Let's just make all of these one bit thicker because otherwise it's just going to irritate me the whole time. The one part is sodium chloride and the other part is then magnesium carbonate. So magnesium carbonate. Right, so we have a sample like that. And we're told then that, well, this sample is going to be heated and there is a gas that forms, CO2 forms. So there's a process whereby temperature is increased, so heated or heat added, we indicate that by this little delta. And there's going to form a gas. So there is plus CO2 gas that forms here. But we should also have something left in the sample. I mean, it makes sense that this sample then is still going to contain sodium chloride. So part of it is still sodium chloride. But CO2 can only come from magnesium carbonate. So that means the magnesium carbonate must have been converted to magnesium oxide during the heating process, and there's only magnesium oxide left. So let's give it a different color, this one. So there's only magnesium oxide left, as well as CO2 gas. And we can see we can actually write a chemical equation from this, which I'll do in a moment. But we're then given some information about this gas that forms. So the information given about this gas is that it is 10 liter of this gas is collected at a pressure of 755 torr and at 20 degrees Celsius. And of course, 20 degrees Celsius is 293.15 Kelvin. So that's the information we're given about the gas that is collected. So let's just write a chemical equation because then we need to balance some things and completely see where everything's coming from. So essentially what we have is we have that sodium chloride, which is in the solid phase, and magnesium carbonate, also in the solid phase, is heated, and thereafter nothing happens to the sodium chloride, so we're just left with it plus magnesium oxide in the solid phase plus CO2 gas. And the reason I'm writing the chemical equation is because you just need to check if it's balanced. So yes, the sodium chloride is unnecessary in this equation, but in principle, this equation just illustrates a process. So one magnesium on the right, oxygens 3 and 3, yes, carbon, sodium, and chlorine. So the reason why I did this is because we need to see what is the relationship between magnesium carbonate and CO2. Because we know how much CO2 formed, we were given enough information about that. So we can relate it then back to the mass of the magnesium carbonate, and we can get the sodium chloride. So how do I do those jumps sort of in logic? It's because we know the mass of the sample must be equal to the individual masses of the sodium chloride plus the mass of the magnesium carbonate, right? CO3. And that is given as 50.00 gram. Okay, so that means if we can somehow get the mass of the magnesium carbonate, then we will be able to determine the mass of the sodium chloride. And that's exactly where this equation will come in, because we can get the number of moles of CO2. So the number of moles of CO2 will then give us the number of moles of the magnesium carbonate. And then we can get the mass of magnesium carbonate and hence the mass of the sodium chloride. So what information are we given about CO2? Well, it's a gas. And when you have a gas and you have the information of its volume, its pressure, and its temperature, you can always calculate its amount from the ideal gas equation. So from PV is equal to nRT, we can write N is equal to PV over RT. So the amount of CO2 is equal to the pressure of CO2, which is 755 torr, the volume, which is 10.0 liter, all divided by, now the important point is what is R? And R has different values depending on the units that you use, and we're looking for a combination of liter, torr, and Kelvin, and of course mole, but they all have mole per Kelvin. So you're looking for the units of liter and torr. And I mean, we can see this one will fit nicely. We have liter and torr and mole and Kelvin because our pressure and our volume is given in torr and liter. Hence, we can use this one will be the best suited. So 62.364 liter torr per mole per Kelvin. And then the temperature was 20 degrees Celsius to 293.15 Kelvin. Okay, so calculate that. You will get a value of 0.41, etc. mole CO2. Now we know how many moles of CO2 is formed. We can use this chemical equation of ours to relate that to the number of moles of magnesium carbonate. So, therefore, we know that 1 mole of magnesium carbonate produces 1 mole of CO2. Hence, the number of moles of magnesium carbonate that would have produced 0.41 moles is what we're interested in. So from here we write that the number of moles of magnesium carbonate is equal to, so we cross multiply and divide. So this one goes there, that one goes there, and then we eventually divide by the left-hand side to get the number of moles alone. So it means, it's simply put, I mean, it's going to be 1 to 1, but let's be overzealous and write everything. 1 mole magnesium carbonate per 1 mole CO2. So that comes from the chemical equation. And then multiply that by the real amount of CO2 that we have, mole CO2. So you'll get that from your cross multiplication and division, or you can just write it from the chemical equation. Then mole CO2 is going to cancel, And you will be left then with 0.41, etc. mole magnesium carbonate. Okay, so now we know how many moles of magnesium carbonate we can have. We can calculate the mass of the magnesium carbonate. So the mass of magnesium carbonate is equal to the number of moles of magnesium carbonate multiplied by the molar mass of magnesium carbonate, NgCO3. This value here is 84.314 gram per mole. And this one here is, of course, the 0.41 mole. So you will get 34.8 gram magnesium carbonate. Hence, the mass of the sodium chloride in the sample is equal to the total sample mass minus that of the magnesium carbonate, so 34.8 gram will give you rounded 15.18 gram. Is 15 point, which has to be, that one is to technically 3, 4, 15.2. 15.2 grams. Right. Three significant figures. Actually, no, my apologies. It's from the significant figures here. So adding addition and subtraction, you look at the number of decimal places. So 15.18 is what's the dominant thing. The last thing we did, so that dictates the number of significant figures. All right, so that's a basic idea here. Remember, you can technically write any chemical process as a chemical reaction. There's nothing wrong with that. And that means you can always get some sort of mole ratio for the species that you're working with. And hence, from that, you can gain a lot of information. Okay, thank you for watching.